Hi class, welcome to Unit 4, Lesson 8. We'll look at diffraction of light through a single slit today. So today's learning goal, students will just demonstrate an understanding of diffraction of light through a single slit and resolution. And I know if I've achieved these goals, if you can describe in detail diffraction of light through a single slit, the formation of bright and dark fringes and resolution, and investigate the relation between wavelength and width, to solve problems related to diffraction of light through a single slit, and apply learning to daily life problems. So we talked about Young and his two-slit experiment. What happens with a single slit? Well, light passing through a single narrow slit is diffracted, just like with our water waves. Remember, through a small aperture, it was diffracting in the obstacle, and the extent of the diffraction increases as the narrower and narrower slits are used. Just like the same thing, we said that when we were narrowing that gap in the obstacle, we would get more diffraction with that lambda over W is greater than or equal to 1 ratio. However, interference also occurs. The figure shows that a pattern of bright and dark lines appear if a screen is placed on the far side of the slit. The pattern consists of a bright central region, the central maximum, which is this region, and then with dark regions of destructive interference, here and here on either side, and then alternating with progressively less bright areas, which are the secondary minimas here, or maxima. And then it continues as you go on and on. Although this pattern is somewhat similar to Young's pattern, the spacing of the bright and dark areas are very different, and so we'll need, if we're interested in calculating them, we'll need to do some extra work. So as we showed in the diagram, the central maximum is the bright central region in the interference pattern of light and dark lines with this diffraction. The secondary maxima is the progressively less intense bright areas on either side outside the central region in this interference pattern. And the term monochromatic means that it's composed of one color possessing only one wavelength, which we'll come to see in some of the other slides. So to see how this interference pattern arises for light, we can analyze the wave behavior of monochromatic light passing through a single slit. So say a single slit is illuminated by monochromatic light, we can consider it a row of point sources of some finite number, say 12, and say that they're close together and vibrating in phase. Each such source may be regarded as producing individual secondary waves. And what does this sound like? Do you remember the secondary waves that we talked about with Huygens and how we would make a new wavefront? And so we'll use these wave rays to represent the direction of motion of the individual Huygens wavelets. A screen on the far side of the slit shows an interference pattern, which is the sum of the contributions from each of the point sources. And these various point sources generate both constructive and destructive interference because of the different phases of oscillations reaching the screen over different distances. So first, let's look at the rays that pass right through that produce the central maximum. So since the rays from all 12 point sources are all start in phase and travel approximately the same distance to the screen, they arrive essentially in phase. And so we have constructive interference because of this. The relative phase is 0. And so when they're constructively interfering, it's producing this really super bright area, which is the central maximum, as we mentioned. So notice here, all 12 travel the same distance, uninterfered, and with nothing affecting their distance, and so they all travel the same distance to the screen. There's no sense of diffraction or anything, and so they arrive at the center of the screen, constructively interfering and make the brightest part of the entire strip. Now let's look at the case of the waves of light that are diffracted downward through an angle, which looks like figure A here. So notice that waves from the top of the slit, point 1, travel farther than waves from the bottom, point 12. If the path difference is one wavelength, the light rays from the center of the slit will travel 1/2 wavelength farther than those from the bottom of the slit, and they will thus be out of phase, producing destructive interference, which we've seen before. So that means that if this, notice this is lambda, this distance, extra distance that one is traveling, the 5, 6, 7 middle wavelengths, labeled 5, 6, and 7, are going to be traveling an extra lambda over 2, half wavelength, and these ones in the middle are going to cause destructive interference with the other ones, because they're traveling half a wavelength more as opposed to a full wavelength. And so similarly, when waves slightly above the bottom, point 11, and slightly above the central point, they start canceling each other. In fact, the ray coming from each point in the lower half of the slit will cancel the ray originating from a corresponding point in the upper half. So corresponding, so we get this, each one is having a corresponding one it's destructively interfering with. As a result, the rays will interfere in these destructive interference patterns or pairs, causing a dark fringe to appear on the screen because all these have a corresponding pair that they're interfering with destructively. In the same manner, destructive interference at an equal distance above the central maximum. So as we can see from figure A, for the first minimum, first dark spot, we have a path difference of 1 wavelength given by this expression. And so in the previous one, we said sine theta was equal to 0, which resulted in a bright and there was no phase difference. Versus this one, we're saying that sine theta here is equal to lambda w. And for when we have that, that means we get dark spots because we get these pairs that are destructively interfering with each other. And so this is the formation of the first dark fringe because of this destructive interference in these corresponding pairs. So what happens if we continue to push this theta value down even more? So we started with theta, we had a theta equals 0, and then we had a theta 1 equal lambda over 2, or half lambda. And then what happens if we have a theta 2 and brought that value to 3 over 2 lambda? Well, we find that we have this effect of corresponding point sources, except this time now we have constructive interference. So we find that each point source in the bottom third of the slit, we're going to have a corresponding point source in the middle third that is half a lambda farther from the screen. These pairs of point sources interfere destructively, but the waves from the top third of the slit still reach the screen roughly in phase, which yields a bright spot. So this time, instead of having pairs where you have, when they're in phase, they're constructively interfering, or having pairs that are destructively interfering, we have thirds. And so we have point source from one from the bottom of the third corresponding with the middle third, and they destructively interfere. But then the last part of the last third from the top third, it combines with the result of these two thirds and is enough to, when they're added up, there's enough of a crest or trough to overcome the opposite smaller magnitude coming from this combo, and we get this bright spot. And so the bright spot is not as intense as the central maximum because most of the light passing through the slit at this angle is given by this expression, which has value. It's not 0, as we saw. When we have sine theta equaling 0, that's when the brightest point is existing. So since we have some value here, it's not as bright. It's less value than this, since our sine theta 1 here, it's going to be closer to this value will be closer to 0 than this value. So that's why it's brighter, but it's still not 0. Another way of seeing this is that we have these corresponding pairs, but this time we have thirds, and so instead of these two, just the destructive interference ending here, we have a third piece, and when it's added up with this 0, we have enough wave to make a bright spot, as opposed to if we just had this. These two is the same scenario as the first dark fringe here, but because we have another third of something to add to this, we have a net bright spot. But obviously, because we have some destructive interference, it's not the same as our first scenario where we had the brightest maximum. So we have a case in between the two here. And so if we push this theta to even further to a theta 3 we'll say, we see the formation of the second dark fringe, because the top waves, which are traveling an extra distance of 2 lambda, farther than those compared to the bottom of the slip, and so we get a second dark fringe formation represented by this expression, and a second line of 0 intensity occurs in the diffraction pattern. And so when we combine our data here, we see that our maxima, or bright fringes, occur at values of sine theta equaling 0 was our first example, and our first bright fringe after the here was our brightest maxima at 0, and we had it equal to 3 lambda over 2 W was our next one, and so that's what we have here. And then the next one would be at 5 over 2 lambda over W, and on. And so in general, we can say that sine theta n equals m plus half over lambda over W will always be our maxima. And likewise, we put our data into what we saw. We saw the first dark fringe is at a value of sine theta equals lambda W. The second one occurred at 2 lambda W. So we have our 2 lambda W. Next one would be 3 lambda W, and on. And if you continue the pattern, we can see in general that the minimas or dark fringes occur at sine theta delta n equaling n lambda W's over W. And so we come to these important general formulas. Our maxima and our minima here. And so we define the variables in here. We have theta is the direction of the fringe, lambda is the wavelength, W is the width of the slit, and m equals 1, 2, 3 is the order of the maximum beyond the central maximum. So if we said m equals 1, that would correspond, we put it in our formula, we would have 3 over 2, we would get this is what we get when we do m equals 1. and this corresponds to the first bright fringe. We get this value, it's the first bright fringe, not the central maximum. It's the first bright fringe away from the central maxima. So that's what we mean by the first order of maximum beyond the central max. So here we can just outlay what it looks like. Again, here's our central maximum, the brightest one. Right here. Here is m equals 1, our first order maximum beyond the central maximum. M equals 2, m equals 3, and on. And this is the same, m equals 1, just in the other direction. We're just rotating up or down. We have that. Whereas our values of n would be the dark spots in between, but because they're just the same value of darkness, we're more so interested in the diminishing brightness of the maxima. But the n's would go in there, representing the dark ones. And here is just a nice graph version of intensity versus the sine theta, with the interference pattern mapped right along it. So we see our brightest maximum is obviously our brightest intensity, and then it comes down as we have our destructive interference at when we have a sine theta equal to lambda w, as well as the negative version in the other direction. It's the same thing, rotating up or down. And then as we come back up and rotate further down, we get our second maximum, because we get those thirds that we're talking about, how 2 of the thirds are destructively interfering, but then the last third is enough to make a maximum. But obviously it's not as bright as having 2 maximums work together in phase. And so we see our alternating dark and bright and diminishing brightness in the maxima as the order goes down or goes up, the m order. The last thing to notice is the distance between maxima or extrema is delta y we have. So between all other orders, we have delta y between the first maxima and the second order maximum, as well as between dark spots. We also have delta y, one distance of 1 and delta y, and after the second and third dark spots. The only area where we have difference is the first central maxima, which is 2 delta y wide here. And that's why we have 2 delta y, a maxima of 2 times the size, versus everything else is delta y. The central one is 2 delta y. So now let's look at the relation between wavelength and width. The width of the central maximum is defined by the first minima on either side of the center line. For the position of the first minima on screen, we have sine theta. What value does it have? It occurs here. First dark spot, right? First minimum is lambda w. So we can say that this sine theta is equal to lambda w. We've said that This is equal to, in the past we've said x over L. The distance we used was x. But in this case, the distance is the same as y1 here. And so we can say that instead of x over L, we can say y1 is over L equal to this. And then we want to rearrange for lambda. Yeah, lambda is equal to w y1 over L. But y1 is only really distance between the first dark spot and the center of the extreme central minima, maxima. So we want to kind of change this to something more universal and not just have y1 there. And so we made a note that every distance between extrema, like this maxima and this maxima, is y1, or delta y in this picture, is the same as y1, as well as that of the dark spots between here and here. For this picture, it's the same as y1 and delta y. And so everywhere except the central maxima, we see delta y equaling y1. The size of this extrema is that only in this central area is that not true. So we can say that since the separation of the maximum minimum delta y outside that central area is the same as y1, which we just noted, then we can then take this that has y1 in it, and since we said y1 is the same as delta y everywhere except that central thing, we can write it as this, which is a lot more, delta y is a lot more useful than just y1 in one area. And so we have this very powerful formula where w is the width of the slit, delta y is this distance between the extrema, or really the size of the width of these extrema, and L is the horizontal distance to the screen. And so we have this very excellent formula that we can use for problems. So we have light from a laser pointer with a wavelength of 6.70 times 10 squared nanometers, passes through a slit with a width of 12 millimeters. A screen is placed 30 centimeters away. How wide is the central maximum in degrees and centimeters? So we have a lambda, a slit width, W, we have our L given, that horizontal distance, and so we want to look for, in degrees, we're looking for a theta. How wide is it angularly? So we know that the central maximum, its size is defined by the width of the, the width of the central maximum depends on where the dark fringes are lying, the first order ones, right? Because they're the first, the endpoints of that central maximum. So we can see that a sine theta value of lambda w is the endpoint of this central maximum. And so if we find that theta value out of that sine theta value of lambda w, that'll give us this half. And so we'll just need to get the other half by multiplying by 2, since it's symmetrical, to get this other half. So how do we do this? So we take, based on this graph, we have a sine theta value. The endpoint is at lambda w, which we saw here. So if we take that formula and we plug in our known lambda and width, convert it to the same unit. We then get 5.58 times 10 to the negative 2, sine inverse this value, and we end up with this theta. And like we said, this is this half. So we need to multiply by 2 to get the whole angular width of the central maximum, which is 6.4 degrees. Now to find that in centimeters, that's y. That's this value y1 here. And again, this is only half of it, so if we want to find this distance in centimeters, we need to find y1 and multiply by 2. So we get this other half, and we get the full size of the central maximum. And so before we said that sine theta was equal to y1 over L. So we use this formula here. And we rearrange for, we want y, we know L, and we just found out the theta from last time. The theta that gives us a sine theta value of lambda w, which is the first order dark fringe. So we take that theta corresponding to that first order dark fringe, and we put it into this right here. We give our given length, we come up with a distance of 1.67 times 10 to the negative 2 meters. We can convert it if we really want to, but the important part is that the width of the central maximum is 2 of this y. So we multiply whatever it is by 2. Because, like we said, central maximum is y1 is 2y this of size. And so part B, what is the separation of adjacent minima, excluding the pair on either side of the central maxima? So what is this asking? That the separation distance of adjacent order minimas, maximas. Well, we said that is delta y, right? Between, it's the same distance for adjacent minimas and maximas, excluding the first one. So that's why we have an excluding the pair on either side of the central maximum. We're talking about the other ones, which all differ by delta y, as well as here, here, and on. So we're looking for delta y, the separation of adjacent extrema. And so we also said that beyond the first central maxima, we went from y1 being able to say that delta y is the same for all extrema beyond that first central one, because it's double. So we can use this formula here for everything beyond the central maxima. And so that's what we do. We do lambda equals w delta y over L, where we want the separation or distance between the extrema, and we're given our L, W, and lambda. And so the calculation is excellent. We have our units all matching, and it comes out in the same units, a value of 1.7 times 10 to the negative 2 meters. And so we have the separation of adjacent minima and other adjacent extrema, except the first one, the central one, is 1.7 centimeters, or this is fine too, in meters. And the central maximum is exactly twice the width of the separation of other dark fringes. What this is really saying is that the central maximum is twice this separation distance. So what is that? And what is the separation distance? It's delta y. So we're just saying that the size of the central minimum or central maximum is 2 of this delta y. And we know this to be true because 2 times delta y is the size of this central maxima. And so what we've seen happen here is we've confirmed how equivalent these two are, and that our thoughts here of y1 and delta y being the same size is valid because we're asked to find, when we're asked to find how big the central maximum was, with the information we had, we found y1, which is half that, which is the distance from the center of the central max to the first dark fringe, right? This distance, so y1, right? And then we found, we had to look at the separation. What was the size of the separation between extrema, specifically minimum, but it's the same for all the extrema. And so that was delta y, and we found that it was the same value. And we know that that's true, that this distance, y1, is the same as delta y, and this delta y, or y1, is the distance between all extrema, all adjacent order extrema. So you have these adjacent dark points as well as the adjacent light points, and that differed, as we saw here. Delta y is the same as that y1, so we're just confirming it. So what does that also mean is we have two methods of calculating the size of this central extrema, by either going the y1 route, or we can go the delta y route. And we can also, if we're given information about the central extrema, we can extract y1, and we already know that it's the same as delta y, and use that separation distance for other places like here and here. So we've kind of confirmed our formulas in work and how delta y is the same as y1. And so based on the information in your questions, you may have to go this route or this route, depending on what information the formula are given, but you can find that magnitude delta y or y1, and then use it to find the size of the central maximum. So what happens if you do this through a pinhole, which is a very tiny circle, versus a slit that we were looking at? Well, you get the same interference pattern with our extremely bright extrema center in the middle, just radially outwards. So we have our first dark fringe, and then our first order maxima away from the central maxima. Notice it's lighter than the center one. And then we have second order maxima. It's dimmer and dimmer as we go. And so it brings us to resolution, which is the ability for an instrument to separate two images that are close together. So if you notice here, object 1, object 2, the camera aperture captures them, and if they're somewhat apart, it doesn't have a problem. Both patterns are nicely distinguishable, they're not interfering, and we have one solid circle, and the other solid interference pattern. And notice there's no mess here. We have very clear, we can see both of them very clearly. But if you bring them closer together, they start to overlap. And if you bring them even further closer together, all these points start to interfere with each other, and you get something like this, where now you have interference between the two patterns. You have this is object 1 and object 2. You have object 1's pattern here and not interfered with, but close here and here we get interference, and these aren't the original patterns being emitted by object 1 and object 2 here. You wouldn't have these original things. You have them now pushed together, and now you have barely resolved, and you'll barely be able to see the distinct objects patterns. So diffraction limits our ability to resolve closely spaced objects because it causes the images to overlap. And this is what sets a limit on what objects from on Earth that can be imaged from space, is this interference, and you get things like this where we can barely resolve them. And so we can also see this in headlights. If the car is farther and closer to the camera, so if your capture point is, your lens would be capturing something like that, and it wouldn't change. It stays the same, roughly. And so by moving distance back, we have, say, our light source is here from A. As we move the car back, we notice that these get closer together, and then so much so that they're so close together that we get this interference, so we can't even tell that it's two sources. So it's the same. I should emphasize it a little bit better. This distance being pushed in more and more causes more and more interference until they're like distinguishable, indistinguishable. Because as the car moves back, it's basically like pushing the headlights together more and more close together, and so they interfere much more, and we get this, we have reduced resolution of for the camera. So at this distance, the camera is able to has a higher ability to resolve things, and at C, when the car is much farther back, the camera has a reduced ability to resolve the different sources, the two sources. And that's the end of the lesson today.